All right, hello. My name is Ed Platt, and today I'll be talking about how large groups make decisions. This is work that I did as part of my PhD with my advisor Daniel Romero at the University of Michigan School of Information. When I say I want to talk about large groups and decision making, I mean groups like worker cooperatives, hacker spaces, maker spaces, as well as social movements like Occupy and online platforms like Wikipedia. Now, I study these from the perspective of network science. So I study the shape of who talks to who. For example, if we have everyone sitting around a single round table, everyone can talk to everyone else, and you can model that as a complete network. On the other side of the spectrum, if you have a more hierarchical structure like a corporation or military, where everyone has a single superior and some number of subordinates, you can model that as a tree network. Now, when studying these groups, that there tends to be a trade-off between participation, how many people participate in a decision, and discourse, how much back and forth there is in that decision. So in the lower left, we just have individual decisions, so that might be a dictator. In the lower right, we have something like the US Congress, where you have a very discursive body that is deliberating and having conversations, but they're limited to a very small size. So what is the alternative to that? Well, as you scale up, you can move to something like ballot initiatives. So that's much easier to do at a large scale, but you lose the deliberative back and forth. But what we've seen in some of these internet-enabled groups is that the internet is making things in this upper right possible. As part of my PhD research, I looked into what is special about the internet that enables this, and what I call it is network deliberation. This is a model of a common structure that I've observed in all of the groups that I've studied. And what does that look like? Well, let's say we take a large group and we divide it into smaller subgroups. I'll call them pods. So here we have a large group divided into pods of 3. Each of those pods has small group dynamics, so they can have conversations, build trust, but they're informational silos. They can't interact with anyone outside of their pod. But here is the key part of network deliberation. You can allow members of one group, one pod, to belong to other pods as well. And those create links between the different pods and allow information to diffuse throughout the entire network. And that allows this best of both worlds situation with small group dynamics, but also allowing information and ideas to travel quickly through the network. So the specific work I want to talk about today is a computer-based model to try to understand how and why network deliberation works. So first of all, we need a task to simulate. And we do this by defining an objective function. So agents have a state x. It could be anything. And there's some function q, and the agents want to find the x that maximizes q. That is their goal. And they're potentially working together to do this. So that is our model of deliberation. So in particular, we're focusing on objective functions that have what's called a rugged landscape. They have multiple local maxima. And this mimics the structure of a lot of real-world problems. So this is the type of problem that we want. So it has local maxima. It also has a basin of attraction for each of those local maxima. And what that is a region of possible states that eventually converge to a particular local maximum. So agents who are in different basins of attraction will converge to different local maxima if they're working independently. The specific model we use is called the NK model. It's well known in complex systems. It was introduced by Kaufman and Levin in 1987. The state here is a binary string of length n. That's where the n comes from. And the fitness The Q function is actually a sum of terms, and each term involves k plus 1 of those bits. So that's where the k comes from. And the bigger k is, the more rugged the landscape is, the more local maxima you have. Okay, so what does the behavior of the agents look like when we're simulating these? So we start with some number of agents. We assign them a random state to begin with. We then place them on some type of network, and we allow them to interact and improve their beliefs and their states based on those interactions. And they can use multiple possible strategies to do this. And they can use different types of information about the solutions. So one possible option is to use the best neighbor algorithm, which is simply to look at the neighbor who has the highest valued solution and adopt that solution. Another option mimics social influence, and that's called the conform option. In the conform option, agents find the most popular state and conform to that state. But we also apply individual learning, incremental improvements, to see if they can flip one bit to find a better solution. And in our network deliberation models, we then shuffle the network. We reassign members to different pods. And then we repeat these iterations until the solutions are stable. So what do we see? Well, so here are the results for the conventional networks. We use preferential attachment and small world networks to represent conventional large single group deliberation. And you can see best neighbor performs pretty well. Confident neighbor is a variation of best neighbor. Conform performs significantly worse. Let's see what happens with network deliberation. So for the network deliberation networks, performance is comparable for best neighbor and confident neighbor. But for the conform strategy, the network deliberation networks perform much better, and they actually perform as good or better than best neighbor, which is really interesting because the conform strategy uses strictly less information. So somehow they're performing better with less information. So what's going on? Well, one thing we can look at is how agents are moving between different basins of attraction. So what we see for preferential attachment and small world, the conventional networks, is that the convergence is pretty quick and that there's about an even split between moving to better or worse basins of attraction. We also see that as time goes on, the number of agents who could move to a better solution seems to level out at a non-zero value. So this tells us that agents are conforming very quickly, but they're not conforming to the same solution. Now let's compare this to network deliberation on the right. So the convergence is just a little bit slower, but the agents are slightly more likely to transition to a better basin. So why is this? Well, the longer agents are able to explore, the better information they will have about the value of their basin, the closer they will converge to the local maximum. So we do see a quick convergence here, but agents don't get stuck. They continue exploring and evaluating their basins and eventually may switch to a better basin. So what we actually see happening here is that the conform strategy causes an information cascade where agents conform to a particular solution because it's popular, not because it's better. And network deliberation breaks that by allowing agents to be exposed to diverse viewpoints for a longer period of time before they make up their mind and get stuck on a single solution. Okay, so thank you for taking the time to watch this video, and I hope this helps you understand how large groups make decisions a little better.